Sejam todos bem-vindos à FGV. Seu evento vai começar em instantes. Antes do início, por favor, pedimos para que se atentem às orientações a seguir. Lembrem-se de colocar seus celulares e equipamentos eletrônicos no modo silencioso. Não é permitido que sejam consumidos alimentos e nem bebidas no interior do auditório. O limite máximo de público é de 150 pessoas. Este auditório possui lugares reservados para cadeirantes e para pessoas com deficiência auditiva e visual. É proibido fumar em todos os ambientes da FGV, conforme Lei Federal nº 12.546 de 2011. Em caso de falta de energia, as luzes de emergência acenderão automaticamente. O espaço possui saídas de emergência sinalizadas, com portas equipadas com barras antipânico, que possibilitam a saída do local com segurança. Para abrir a porta, basta empurrar a barra. Este ambiente conta com equipamentos de prevenção e combate a incêndio, como detectores de fumaça, extintores e hidrantes. Em caso de emergência, a brigada de incêndio será acionada para ajudar. Siga as orientações da brigada de incêndio. Ao ouvir os alarmes ou mensagens de emergência, mantenha a calma, evite pânico e confusão. Em caso de incêndio, não use o elevador. Desça pelas escadas de emergência. Para maior segurança, este auditório é monitorado por circuito fechado de TV. Antes de sair, confira seus pertences para não deixar nada para trás. A FGV não se responsabiliza por objetos deixados ou esquecidos nos auditórios ou em suas dependências.
Antes de darmos início ao evento, gostaríamos de reforçar o seguinte disclaimer. As manifestações expressas por integrantes dos quadros da Fundação Getúlio Vargas e por convidados que participam dos eventos e transmissões online representam exclusivamente as opiniões dos seus autores e não refletem, necessariamente, a posição institucional da FGV. Este evento poderá coletar seus dados pessoais e registrar sua imagem e voz por meio de vídeos, respeitando as leis aplicáveis. Você poderá deixar de participar do evento. Em caso de dúvidas, entre em contato com a FGV pela aba de proteção de dados no portal.fgv.br. Agradecemos sua participação e desejamos um excelente evento.
Nós somos o Centro de Estudos de Infraestrutura e Soluções Ambientais, o FGV CEISA, da Escola de Administração de Empresas de São Paulo da Fundação Getúlio Vargas. Um espaço que conecta especialistas, acadêmicos, profissionais do setor privado e representantes do poder público. Ao longo dos anos, promovemos encontros e debates sobre infraestrutura, ESG e economia circular. sempre com o propósito de impulsionar o desenvolvimento sustentável e influenciar políticas públicas de impacto. Confira os nossos próximos eventos.
Bom dia a todos. Nós temos hoje um grande evento, onde o professor Kartik Chandran é o nosso convidado. Nós temos debatedores muito especiais, aqui a professora Ana Silvia e o doutor Alexandre Setivaras, para coordenar os trabalhos o doutor Adriano Stringini, nosso Senior Fellow aqui do Centro, e o nosso colega, professor Sérgio Goldbaum. I will turn to English now and say that we are very thankful to Professor Kartik Chandran to be with us this morning. Kartik Chandran is an engineer, an environmental engineer, a professor of the engineering department of Columbia University. He is one of the best experts in the world in terms of innovation in water and sanitation, and also he has led different projects of circular economy in the field. We are very happy to have you with us, Professor Kartik, and to have the comments and also very good insights from Professor Ana Silvia, who has been working with water for reuse at the University of Minho in Portugal. She's in Braga at this moment. She's actually, I presume, talking from Braga in Portugal. And Alexandre Setivaras has a tremendous experience in the solid residuals sector in Brazil. He has been executive of very important enterprises in the field. Mr. Adriano Stringini has a vast experience in water and sanitation. He was director of Sabesp for more than 15 years. And Professor Goldbaum, who we all know, is very active at the Center for Infraestrutura Studies, and he has been engaged in several projects in the field of water and sanitation and environmental solutions in general. So, Professor Kartik, great pleasure to have you. We want to have this conversation today, but this is a continuous conversation. We would like to maintain a regular contact with you and with your projects and of course, take advantage of the privilege of having your generous time to share with us your recent work. Thank you very much, Professor Kartik. You have a presentation. I will accompany your presentation, and after the presentation, Mr. Adriano will lead the meeting. Thank you very much.
Mr. Justin, thank you. It is my sincere pleasure, and very nice to meet colleagues in Brazil and Professor Ana Silvia in Portugal as well. I'm truly sorry I'm missing such a nice event. Just to give a brief background, my two students, one student and one postdoc, are actually now in Brazil in Fortaleza, and I think I was the only one who missed that flight. But then, as Professor Jasner mentioned, I would very much like to contribute to building something more. We've been interacting for, as I look back, more than a decade now, and yeah, I look forward to doing this and having an impact going further. So I will share my presentation, and it's just to spur and catalyze some discussions going forward today. Are you all able to see the full screen? Yes, thank you.
Yes.
Thank you. Okay, so to be consistent with the theme of our discussion today, the focus of what I will present is on some innovative approaches, technological approaches and otherwise, that are able to accomplish increased access to water and sanitation. There is indeed a focus on in remote environments, but that term remote can apply not just to geographically distant communities. Remote could also mean certain inaccessible parts of even cities which are existing now. So remote could be packaged or viewed under different lenses as well. And so when we talk about wastewater treatment, sewage treatment, from just strictly from an engineering perspective, this is something that might be familiar to some of us, all of us. Essentially, what we do is as follows. We take out, let's say, the solids, the primary solids, the inerts, and so on, predominantly by gravity, by settling. There might be some chemical addition if and as needed. And essentially what happens is anything else that is soluble or below a certain particle size or molecular weight, it is essentially passed on to the biological reactors. And these are really the microbial factories where all the activity, all the transformations are happening. But if we just peel open some of this, essentially what we are doing in these centralized treatment plants is that we are essentially providing air. We're providing oxygen, which is in air, to convert the organic carbon to carbon dioxide. And if there are regulations, if there are limits, then the nitrogen and phosphorus also get transformed if there are limits. Otherwise, then they just get passed on to the environment. And then finally, what we do is we settle the bacteria that we have. If I move my mouse, can you all see my mouse as well? This arrow, if I do this? Yes, thank you. So what we have done in this schematic is that we have produced more organisms. The bacteria that consume the carbon, nitrogen, phosphorus, they have also replicated. And so we don't want to discharge those bacteria. And essentially we settle the bacteria and we send them back. And then the treated wastewater gets discharged into the environment. To give you numbers, in the US, only about 5%, 5 to 7% of the water that is used is actually from a circular water model. Otherwise, it's all a linear model. And a model like this also is part of that linear model where we treat wastewater, but then we discharge the treated wastewater into the environment. Now, let's take a look at the footprint of just this process here. That all of this is not free, obviously. The bulk of the energy that is consumed in a wastewater plant, treatment plant altogether, the bulk of it comes from this one particular process. And within that, it comes from one particular act of providing aeration. And this is what essentially precludes the vast majority of the world today from accessing a model like this. There are other implications as well. When things do not go as planned or as designed, these reactors also produce other gases, including greenhouse gases, such as nitrous oxide, which is a substantial challenge. Again, to give you numbers, if we take the worst performing plants in the US in terms of nitrous oxide, greenhouse gas production, they may be treating the wastewater to a certain degree, but if we take the worst of them and we apply those numbers across the US, that nitrous oxide footprint is equivalent to roughly 100 million cars in the US per year. The the population of the US, for reference, is about 330 million. And if you're saying that, one car per individual, we are talking about a substantial contribution of this model of wastewater treatment to not just clean water is fine, but the energy input, the greenhouse gas emissions. So this is not free by any means. But it is important to keep in mind, just to move forward positively, who are the organisms doing all of this? It's the microorganisms, the microbiomes. So therein lies the opportunity for us to do something different, something better. So if you just take a look at the overall picture, this is not recent, but this is the overall picture for wastewater treatment around the world, access to wastewater treatment. This is from the UNEP and also shared by the International Water Association. Anything that we see in blue is more positive than anything that we see in orange. The overall picture is not something that is not familiar to us. We know that the picture of water and sanitation is quite challenging, and that's essentially what this is doing, what this is describing. Let me take you to a first-hand view of what I have seen. So coming from here, what do we try to do? We try and install and implement technologies to overcome that challenge. And so this is actually a photograph from a treatment plant in Accra, in the country of Ghana, in Africa. The plant is very good. It's technologically very, very appropriate, technically appropriate. On the other hand, the plant does not do anything. It is not because the technology is not working. It doesn't do anything because it does not receive enough of the wastewater flow. And when we talk about remote, this is why I wanted to also put that term remote in perspective. This is in the city of Accra, which is the capital of Ghana. So it's not remote by any definition. On the other hand, when we talk about access of a technology to the stream that it is supposed to be treating, it is remote because there is no connectivity. And let me tell you actually what is happening. Can you see this discoloration here? This brown discoloration. So this is a photo that I took when I was flying out of Accra. And this plant here on the left-hand side sits very near the coast here. The plant is not doing anything. All the fecal sludge is getting dumped into the Atlantic Ocean. And it is because of two aspects. It's not because the technology is bad. It is fine. It's just that the waste gets transported in trucks to reach this plant, and the trucks are just coming and dumping the fecal sludge into the Atlantic Ocean. That's one. So the plant doesn't get anything. And even if the plant gets something, these numbers are meant to convey the simple message that these plants, some of these plants consume a lot of energy, and some of these nations do not have enough energy to devote to these very energy intensive, energy expensive models of wastewater treatment. So that's the other thing, that's the other challenge that we must contend with and overcome. So let's go back to this. Let's go back to this model and try and at least frame the problem here. Instead of taking this model and putting in even more resources to treat wastewater and only for it to be discharged, or worse, as we saw in the last slide, just dump it into the environment without any treatment because of the lack of energy. Is there anything else we can actually do? Is there a different way of looking at this to prevent such occurrences? The answer is yes. If we take a look at what is coming in, and if we take a look at what is coming in terms of carbon, nitrogen, phosphorus, the chemical states in which they come in, the answer is a big yes, is a strong yes. Essentially what we can do is that from these different waste streams, we can start to think about producing energy, not just biogas, but higher endpoints of energy. And I'm very happy to be presenting this to an audience in Brazil, which has always been a leader in terms of ethanol manufacturing, advanced fuels, next generation fuels, and those fuels do not have to come from the agricultural side. The feedstock doesn't have to be agricultural waste. It can be domestic waste. It can be municipal waste. Carbon is carbon. Nitrogen is nitrogen. And so we can think about producing different forms of energy, not just biogas, bio oil, and so on and so on. And we can also think about the manufacture of chemicals as well, because treatment is also wastewater treatment, sanitation also consumes a lot of chemicals And these chemicals can be produced from within based on the streams that come in. This can be done. This map also gives you the different locations where things can be pulled out. And so right in the influent, without settling everything and dumping into the environment, we can recover something. As I mentioned, this is the microbial factory. This is where all the activity is going on. Instead of producing carbon dioxide and nitrous oxide, we can channel these microbiomes to produce energy and chemicals. We can do so here as well with another stream that comes out. And here, depending on the size, we can recover hydraulic energy and so on. And when we do all of this, if we do this properly, there is enough carbon, there is enough nitrogen, there are enough resources in these waste streams such that clean water becomes a side product, a byproduct, becomes a bonus. So it's not just treating water for the sake of discharge into the environment. Now this water can be reused as well. Reuse can take the form of many forms. It doesn't have to be potable reuse at all. It can be for industrial purposes. It can be for irrigation. So that perception of drinking sewage goes away as well. In fact, we drink a very, very, very tiny fraction of what we actually consume in terms of water. We use water for so many objectives. The potable fraction is very, very less. That we can continue to get from our conventional sources. The water for other objectives. For instance, we don't have to flush our toilets with drinking water, which is what we are doing, which is what this model like this can offset. Okay, I'll skip through this in the interest of time. So let's look at the economics. If the economics are not there, nothing is going to make sense. And so I'll give you some numbers. The demand for water and sanitation services is projected to be very, very substantial. And this is probably an underestimate as well. And countries like India, the lack of water and sanitation, which is quite poor even now, costs the national economy quite a bit. And again, I have a feeling this is again an underestimate. But the point is, technologically, this is what the overall sector has been trying to overcome. We need some more enabling factors, as I will present as well. So the business case is there. So then, what do we do? And then finally, I want to just present one direction for us to kind of mull over as well. So there's this whole direction of how do we achieve adequate wastewater treatment for reuse, sanitation. Should we try to build bigger and bigger and bigger sewered centralized treatment systems, or should we go to the other end of the scale, smaller systems which are better connected, which are localized, which are on site, which then overcome this challenge of transportation of waste? There is no one answer to this, and so I think it would be inappropriate for us to say that only the centralized model works or only the decentralized model works. But if we are truly aiming to have an impact of communities that are not connected today, perhaps we should keep our perspectives open to be able to go to smaller and smaller scales and have impact. Smaller treatment systems do not mean that they are volumetrically scaled down. So if I say for 100 people, we need a treatment plant of 100 liters, small scale treatment doesn't mean for one person I need a treatment plant of 1 liter. With proper engineering and intensification, that volume can be very, very, very low. So we're becoming more efficient as well. This is a project that I'm working on to understand for major cities in the world, where is the optimum? What fraction of that waste that comes in needs to be treated in a centralized fashion, and what should we recover? And what fraction should be treated in a decentralized fraction? And in these on-site decentralized systems, what resources can we recover? So what is the model of circularity at large scale and at small scale? Okay. Yeah, so I'm sharing now what an on-site system could look like. The ultimate vision is to develop not a miniaturized to talk in terms of treatment and so on. It is essentially coming down to the development of systems that behave like a household device for reuse. And again, reuse can be geared towards the treatment of different streams that let's say communities produce, or a mixture of these two streams as well, which can be envisioned as well. In some countries, there is now legislation that is promoting, and not just promoting, requiring on-site water reuse. In many countries, especially with new residential construction, this needs to be done. In India, with new residential construction, there's this concept of zero liquid discharge. So none of the water can actually be leaving the envelope. It has to be, everything has to be brought back, and for that we need models of treatment. In the United States also, which is very, very good now, there are 5 or 6 cities that require on-site water reuse. So again, this whole concept of remote, we may not think traditionally that this concept of remote applies to a city like New York City, which appears to be very well connected, but there are limits as populations expand, as there is urban migration within the city from other places into the cities. We can't be digging up the infrastructure and putting more pipes, which is where we need to look at smaller scale intensified systems. So there are all these different enabling factors coming in. I will just present 2 brief schematics here. One which only treats, let's say, the streams that the human body produces, which is what we refer to as the black water, and then a combination of gray water, which is water that we use for other objectives, cooking, washing, and so on, and the combined stream. So the systems that we are looking at could be directed only towards one of these streams or a combination of these streams. But you look at this now, this is all happening within the boundary of a community. And these communities can be completely off-grid, or they can be part of a city where there is not enough access. There are in existing cities. So one of the biggest slums in the world is in the city of Mumbai. It's called Dharavi, and systems like this could be very well envisioned and implemented there. Ironically, in these slums, there are very, very mature and active models of resource circularity, not for water, but for electronic waste and other materials. It is just $1 billion industry. Why can't we include models for water and sanitation, which are circular in these communities as well? Okay, let me now take you to also back to Ghana, where this was one of my first projects, and I designed and implemented a system that treated fecal sludge from the equivalent of 20,000 individuals. So if you see here, you see some of these covers, and you see these tanks here. Essentially, for 20,000 people, the overall volume, the reactor volume for treatment was only about 120 cubic meters, which is not much, which is a tiny fraction of what the volume will be if we design a centralized treatment plant. This treatment plant here was not connected by a piped network. In fact, it was sitting in a dump site where, again, the trucks were coming in, but instead of the trucks just dumping on site, we were putting that fecal sludge into this system. In terms of circularity, the initial idea was to convert the fecal sludge into a fuel, and not to compete with the fuel industry, but to have fuel that we can run the plant using. And so that was the point. So the idea was that it would be a completely self-sustaining treatment plant. That was the initial hypothesis. I just put these numbers here because we designed and ran this plant for more than 1.5 years, actually. But the point is, ultimately what happened is we were not able to achieve full circularity. That was not possible because of the efficiency of the system. It was still an offset. We had also initially thought about making biodiesel. That was not possible because of other limitations, but we learned. And we learned what was possible and what was not possible. But at the end of the day, we had the system running, treating waste from 20,000 people, still producing, at the very least, treated effluent that could be discharged. Perhaps not reused because this is a dump site. We could use the water for washing and so on, but we were discharging it. But the point is, we were able to do this, and this was more than 10 years ago. And so this is, again, not hypothetical. All of this can be done. The way we actually did it was there's quite a bit of there's quite a bit of engineering that went into something like this. We even developed a mathematical model, a digital process model, to describe this decentralized sanitation process. And this table I just put here to show you the distinctions. Again, I'll do this quickly. The point is that there are distinctions between these treatment processes. So these are the parameters that are associated with the treatment process that I'm showing here. And the point is that these treatment processes are quite a bit different in terms of what is happening inside compared to, let's say, a regular wastewater treatment process. Because again, the streams are different. So one note of caution here, it is very good that we are trying to intensify these systems. We are trying to run these systems and aim for recovery of resources, circularity, and so on. But the important thing to recognize is from a technical perspective, technological perspective, we just can't take designs and parameters that we typically associate with wastewater treatment and use them for something more interesting and more innovative like this. So there is room for innovation, there's room for discovery in terms of research to ask and answer some of these questions relating to the distinctions. These are new technologies, these are different technologies, and so to the novelty here as well. Now, what we are doing is let me go back to the concept of decentralized, centralized, and hybrid models. Now we are working with different cities, with different cities around the world. And what we are trying to do is determine the fraction of the wastewater that these cities produce that should be treated in a centralized model like this and in a decentralized model in different locations. So basically, we are now testing different types of decentralized treatment systems as well. These are just a few of the examples that we have tested, and we are testing more as well. So this is where concepts like urine diversion, treatment of gray and black water, and other options come into place. And these are the different options that we are testing. These are the different decentralized systems we are testing for combination with different centralized wastewater treatment systems. So that's what we are doing. And we are quantitatively trying to understand what the implications are in terms of savings in operating costs, greenhouse gas production, and performance. So that's what we're doing. So very quickly, the cities for which we have done this include, there are cities in Asia, in South Africa, in the US, and now we are expanding to some other locations in the world as well. I'm just going to skip this graph in the interest of time. But this is what we are doing now. This is very quantitative, and we would love to see if there are possibilities to work with communities in Brazil, perhaps even in Portugal as well, to understand how existing treatment could be complemented, supplemented with decentralized treatment as communities expand and so on. And so let me quickly take you through the benefits. And so again, to be efficient in terms of time, what I'm plotting here on the y-axis is the savings in energy per unit of waste treated in the decentralized. So the picture I want you to have in your mind is there is the centralized plant and connected to decentralized systems, so upstream. So if we have 1 liter of wastewater that is taken out by the decentralized fashion, there is 99 liters coming into the centralized treatment plant. And so if we have a 1% savings in energy for a 1% offset in flow, the height here will be 100, 1-to-1. So if we take out 1 unit of wastewater, we are saving 1 unit of energy. So that's a 1-to-1 benefit. And what we are doing is, here on the x-axis, I show the different cities for which we have done this analysis. And these different colors represent the different decentralized technologies that we have used. And so what happens again and again that we are seeing for across the board, except this last one, is that the orange bar and the gray bar, which now represent just black water treatment and gray plus black water treatment, these are the decentralized technologies that are consistently superior to the others, compared to, let's say, technologies that just take out the solids or just take out the urine or just recirculate. So what we are showing is, for the most part, technologies that treat black water, technologies that treat gray and black water on site, they provide the biggest benefit in terms of energy use for the overall system, the overall combined system. Unless the centralized treatment plant does not need to remove nitrogen or phosphorus and is an anaerobic treatment plant like a UASB, which is very, very common in countries like Brazil and even in India, actually. If there are UASBs that are focused on biogas recovery, then these two technologies, which are based on urine separation to remove the nitrogen and phosphorus, that is where those decentralized technologies work. See, again, there are details, there are nuances. We just can't say decentralized versus centralized. It is a function of what kind of decentralized technology, what kind of centralized technology, and how we put them together. That is what we are showing here. But the bottom line here is that these technologies allow us to perform at a much higher efficiency than we would otherwise. And with optimizing the process, and again, this is the reference line of 100%. So if we take out 1 unit of wastewater, we save 1 unit of energy. With optimization, we are able to operate at a much, much higher efficiency compared to that 100%. So you see, when we connect the system, it's a different system. So we have other ways to optimize, other degrees of freedom to optimize. And with optimization, we are able to achieve much higher benefits. Okay, what else do we need? What are the other innovations that we need? I've been talking about decentralization, centralization, different technologies. At the end of the day, the bulk of the treatment is still biological. And so there are interesting innovations that we need to focus on. This is some of our work where we use fungal processes, not bacterial, but fungal processes to treat not just conventional pollutants in wastewater, but also some of these emerging contaminants. And some of these streams don't have to be liquid. They can be the liquid that is squeezed out of the solids stream as well. So then we are talking about compounds like PFAS and other compounds as well. So we do need interventions. And so this is one exciting direction within the category of enhanced biocatalysis. So different catalysts, not just bacteria, but bringing in fungi. And here, this project involves both fungal and fenton oxidation. So fungal oxidation and chemical oxidation. What else can we do instead of producing biogas? This is going back to our project in Ghana, where we converted the fecal sludge into these compounds, the volatile fatty acids, and then we converted the volatile fatty acids into biodiesel. Let me go to the next slide. In terms of what we actually produced, again, the point of this graph is to show that for different conditions, what we did with, again, a different biocatalyst, not bacteria, this is yeast. And then using this yeast model, we were able to convert the fecal sludge organics into lipids, into fat that looks like this. And this fat profile is essentially identical to that of commercial oil. So palm oil, for instance. So we are not producing palm oil by cutting down palm trees, but we are producing palm oil through by fecal sludge. Okay, and then there are other ways to do this as well. There are other ways to convert and other end products to focus on as well. But again, the point is not to produce chemicals and fuels and other materials even, which we have done and others have done as well. We can even go to hydrogen. We can even go to bioplastics and biomaterials. Point is not to compete with these industries. The point is to go from zero sanitation to one sanitation, using these as enabling factors. Okay, and then finally, very finally, we need some kind of structure when we are looking at improved access, when we are looking at decentralized treatment. One of the biggest accomplishments in this sector, which is very recent, only started in 2018 when the first standard came out, version of the standard came out, is this development of the ISO 30500 standard for what we are now calling water efficient sanitation systems. So this was one of the biggest developments, and this is the standard. It is available on the ISO website, and this standard allows for consistency in the development of these decentralized, non-sewered, water-efficient sanitation systems. So currently there are efforts. Any time that there is a new technology that is developed, those technology developers need to make sure that their technology is meeting these standards. So again, it gives us some structure and something systematic that we can work with. I'm going to skip through the greenhouse gas section in the interest of time. And so just to wrap things up, what I would like to say is, I think this, as Professor Jessner mentioned, this is just the beginning. There are so many opportunities in terms of looking at the different scales at which centralization, decentralization can work. There are very exciting innovations in terms of directions such as biocatalysis, reactor engineering, and new frameworks such as the standards that have come up give us something more quantitative and systematic to work with. Thank you very much.
Thank you very much, Professor Kartik. This is a tremendous presentation. I could see Anna's face admiring the very good ideas. It couldn't be more useful for Brazil at this point, and I'm sure in many other countries. And let me say, and I'm sure that Adriano and Sergio will agree with me and Alexandre Situaras, we would love to give this space to have a continuous dialogue with Institute, with Anna's Institute, and with the companies in academia, in the government of Brazil, of the state of São Paulo, in order to take advantage of this tremendous research experience and practical experience in different countries and sites. Thank you very much. I turn the floor to Ana Silvia in the coordination to Adriano Stringini. I will have to leave for some administrative and bureaucratic things of Getúlio Vargas, but I certainly want to continue this dialogue, and I'm sure after and even today I will see the rest on the social media. Thank you so much.
Thank you.
And Silvia.
Thank you very much, Jesner, for the invitation, for this opportunity. Hello, everyone. Thanks, Professor Chandran, for this awesome and inspiring presentation and sharing your beautiful experience. For me, it's a really nice and great honor to be here with you in this important debate. When we talk about water and sanitation, we talk about dignity, gender and race equality, and socioeconomic development. So Professor said about India, Brazil, and showed a map with numbers of Caribbean, of not South America, but Africa. So it's our experience also. So I think it's important to talk about dignity and gender and race equality and socioeconomic development. So thinking about the great challenge for the future of water in the world, we must deepen this type of conversation, learn from the experience of others like Professor Chandran, organize our own perspectives in Brazil and plan and act according our reality. So I think Professor knows, but in Brazil, only 50% of our wastewater produced is collected and treated, and just over 80% of population has access to drinking water. So our numbers are terrible numbers. But and about drinking water, in this case, we cannot say we cannot claim that all this water is safe. So the problem is worse. So we have a big challenge in Brazil. Firstly, we must achieve water and sanitation universalization, but also we must guarantee resilience and water security. So Brazil is not the country with more water than the others, as everybody think. So I mean, in developed regions, they have only the second problem. But we in Brazil, we still have primary challenge when we talk about water and sanitation. In this scenario, we have a great opportunity. Professor Chandran said challenge and opportunity. Yes, it's perfect. So we have a big challenge, but we also have a big opportunity to advance on these two fronts. I mean, universalization and water security. So we can do this together and design new projects and new infrastructure in a new era of water. So Professor put a statement that we need to think beyond conventional. Yeah, it is the time for that. It is the time. We have different situations, scenarios, and I think we have a great opportunity to think beyond the conventional. We are in the century 21st, so we have to stay there. We are still in the last century, so we have to advance. I think in Brazil, I don't know if the number is correct, but around 50% of our population live in rural areas or outskirts, suburb Islam, as Professor said. So it's very difficult, of course, but not impossible to solve this problem. But of course, it's difficult. But we have technology, we have experience, we have knowledge. But what is missing? I think we will never be a developed country, developed country with this water and sanitation scenario. So we are in a developing country situation and thinking about developed country, but with this scenario, I think it's impossible. So I took some notes here about the presentation, and Professor said about new regulations, about wastewater discharge. So here in Europe, we have a new regulation, a new directive in European Union to tertiary treatment. So we must achieve nitrogen and phosphorus removal, and of course carbon. Okay, so the map that Professor showed until in America continent until Caribbean. So here, not here because I'm not in Brazil now, but South America, I think this number that I said about Brazil is not so different from the other countries from South Africa. Oh, sorry, South America. About electric energy and consumptions, of course, the water and sanitation sector consume a lot of energy. So, but we can produce a lot of energy. So it's very important to think in this kind of scenario, and not only treat wastewater, collect and treat wastewater. It's for the last century. It's not for our century now. So yes, I totally agree with Professor about think beyond conventional. So we have many opportunities like water reuse. Of course, it's my area, my research area. So, but water reuse is okay, but we have a lot of other things to think. like biogas and sludge and plastic and nitrogen and phosphor fertilizant. Yeah. So we have many opportunities, and I think we have to think wastewater treatment not as a service and as a factory or a industry, that our input is wastewater, and we can produce a lot of different outputs. So I think it's my part here. So I would like to continue with professors in FGV. Thank you very much again, Professor Kartik, for your inspiring presentation. Thank you.
Yes, thank you. Thank you.
Hello. Professor, it's a great honor to be with you here, with us and with our colleagues. I saw a presentation of yours in TED a couple of years ago, and you said that we should have a more holistic view on this issue. And one thing I'd like to have a comment of you is about the connection of sewage treatment, as we could see treated sewage, wastewater, not as wastewater, but as enriched water, I would say, in order to produce energy, in order to produce other elements, as you said, especially in connection with COP30 that we're going to have over here in Brazil. As you probably know, the second main cause of GHG gases in cities are the gases that came from polluted rivers. So if we put a very strong eye on that in treat rivers, of course we are contributing for more than 70% of the population that live in cities, and of course that is the second main cause of GHG gas in cities. So how we could foster that debate on copy on this environmental scenario that you're going to have over here in Brazil?
I am so happy that you asked the question for a couple of reasons. The main reason is that sanitation and wastewater treatment or enriched water treatment as a driver for decarbonization. This is such an important point. I'm sorry to say not many people even understand what you're asking. And this is such a powerful tool that we have to clean both the water, the environment, and minimize emissions. And if I could I just share one slide for very quickly, just to kind of help this? Yeah, let me do that. Okay, can you see it now? Yes, it's this one here. So many years ago, let me take one step back. So around 2006, 2007. My group started measuring greenhouse gases, emissions of methane and nitrous oxide from wastewater treatment plants, designed and operated wastewater treatment plants. And there's a protocol now that we wrote to measure, not estimate, but measure. And one thing that came out of this study was not just we quantified those emissions. And if you look at the 2019 IPCC report, the results from our monitoring studies are actually in that report. And the emission factor that is used for waste sector from IPCC comes from that study that we published in 2010. This is the study. Another thing came out of that report, and it's exactly to what you are saying. We found that wastewater treatment plants that do better job at removing nitrogen, which is what Professor Ana Silvia said, referred to as tertiary treatment. Those plants that remove better nitrogen on the water side, those are also the plants that emit less nitrous oxide. And so this is a win-win if we design these systems, cleaner water, cleaner air. But it is also a lose-lose if we do not do, if there's no treatment, as you are mentioning now, no treatment, it doesn't mean just polluted rivers, polluted water. It also means increased greenhouse gas emissions. So now last year, two years ago, last year, I think, multiple UN agencies came together to promote this concept of decarbonization of sanitation and using carbon credits, looping this back into the sanitation space. So to take the credits, improve the technology, and the technologies will produce less and less, and the credits will go more and more. So this is a real this is real. I mean, quantifying the credits and using those credits to promote clean water and decarbonization. Thank you for raising this point.
My colleague, thank you, Professor. My colleague, Professor Sergio, has some comments.
Hello? Okay. Thank you, Professor Chandran. Thank you, Nalucia. Very timely, interesting flow of ideas. I'd like to make 2 comments and 1 question, okay? So first, I noticed that he used the word waste on quotation marks. I understand this is meaning to say that it's not waste itself. It's just an input to other recycling, reusing process. The second thing is that the idea of reusing water from wastewater treatment are a very timely idea. I think it's very useful, a huge opportunity in remote areas in Brazil, not only in distant areas like the Amazon forest or little communities in distant areas, but also in coastal areas in the state of São Paulo, the developed state of São Paulo in coastal areas. I think there is also an opportunity to use that technology in such communities. But I'd like to mention that today in the morning, it was announced the Nobel Prize in Economics. The Nobel Prize in Economics today was announced. It's Howitt, Philippe Aghion, and the third name I don't remember, but they are about innovation. It's about innovation and growth. And here we are discussing about innovation in such a traditional sector like sanitation, which usually people think there is no innovation in such a traditional sector like water and sanitation. And here you are discussing a very nice innovation opportunity. But in the work of Philippe Aghion and the other 2 Nobel awarded economists, they discuss about innovation and resistance to innovation. And then I'd like to address that question to Professor Chandran, if he faced resistance against his innovation, for instance, in one of the projects he mentioned, like Ghana or United States or developing and developed country, if he faced resistance against such a nice innovation that he's proposing right now. Thank you very much.
Thank you. Again, this is so stimulating, the directions that we are discussing. Before I answer the question you posed, I would just want to say one thing. Yes, indeed, I put the term waste in quotation because if you look in nature, we are the only part of the tree of life that even uses the concept of waste. In other across all the other branches on the tree of life, other than ours, there is no waste. Everything gets turned around, and so I think we have simply lost our knowledge, and that's what leads us to making these mistakes. But I have faith. I'm confident we'll turn it around. Okay, resistance to innovations all the time, every single minute, all the time. So as I think I'm not the only one, all of us probably have faced it and continue to face it. So yeah, how do we overcome this? One big learning was to not go top down technology, but involve, let's say, the knowledge, the needs of the community into which some of these interventions are targeted. So to directly involve the participation of the community that we think we are helping. That was one. But again, linking, it's not just taking a technology and putting it somewhere. It is understanding what the limitations are. If there are limitations in energy, if there are no pipes, why would we put a technology like that only for the fecal sludge to be dumped into the Atlantic Ocean? It's essentially if I can summarize it in one word, in one sentence, sorry, it is essentially understanding that technologies are going to be part of the overall solution, and just keeping that in mind. I would like to add one more point. Sometimes, ironically, regulations become are detrimental to innovation, because once the sector has met the regulation, there is no incentive to go beyond and innovate. So I think we can do better over there. Education from where we are all sitting, that is the biggest opportunity we have to change things around as well.
Thank you very much, Professor Chandran. Please.
Excuse me, can
Yes,
I
please.
complete something?
Yes,
Yeah?
please jump in. You're welcome.
Okay, sorry. Just for the complete the two last ask questions. When we talk about energy, I would like to share experience of Águas do Porto. Águas do Porto is the company of water and sanitation in the city of Porto in Portugal. So this institution called Água do Porto, like Porto water, something like that, okay? So now they are Água e Energia, water and energy of Porto, because they now they have to produce energy from the wastewater system, wastewater treatment, and consume this energy in drinking water system. So they now called water and energy of Porto. I think it's very interesting to think like that, like this kind of institution. And the other thing that I would like to say is about innovation. I think it's very, very perfect. This part of the Nobel Prize about energy and creativity. So I think when we think about sewage system and water system, we always think in linear, like water. We catch the water from the river. Imagine the drawing, we have a river and the catchment from the river and the city and the water treatment and city. And then the wastewater system is the sewage and the collection and the treatment and the river. But it's not like this anymore. Today is different. This concept is wrong today. So we have to think in innovation, in creativity, to think in another alternative water source, like no more only river or aquifer. We have sea, we have water reuse, we have atmospheric water, so glaciers. So we have not anymore only river and aquifer. So I think when we talk about innovation and creativity, we have to think in innovation in the concept of the water system and sewage system.
Can I also add to that, since this is a so interesting discussion? I'll be very quick. So on the water side, with respect to water and energy, it'll be also good, and maybe this falls on us as a sector as well. Instead of and you mentioned, Professor Ana Silvia, the water and sanitation as a service going towards an industry. I cannot agree more with that. If we revamp our thinking or reorient our thinking to being the enterprise of producing water rather than treating wastewater. I think that totally changes. It's not just semantics. It totally changes many, many things. The other point that I would like to make is water reuse today is touching not just drinking or irrigation or irrigation. One of the biggest expected sector in terms of water consumption is going to be the data and the information technology sector. Already the biggest corporations in the world are investing and are making substantial progress in terms of water reuse, not for drinking, not for agriculture, but to just from a process perspective. And we all know how important data is going to be moving forward. And data stands, one of the pillars on which data industry stands is on the pillar of water. And it cannot be from a river, it cannot be from an aquifer. It has to be from these other sources that we are discussing, including wastewater. Thank you.
Hello? Hello? It's nice to be here. Thank you for the lecture, Professor. I'm more a guy of municipal solid waste, more solid waste related problems, right? And the sanitation law here in Brazil put water, sewage, and solid waste together. And we face some very similar problems like the universalization of the final, what we call final destination for waste, or the treatment and everything, right? In Brazil, we have around 60% of the waste of the municipal solid waste is already in landfills, in proper landfills. That's nowadays okay. Besides that, we have 40% of our waste going to the open dumping sites. And there is 3,000 dump sites all around Brazil, mainly in the poor areas and small cities in the northeast and the north, right? Where people also struggle with water and the sewage treatment, right? And try to put up proper solutions for these areas is really a very hard technology path for waste, for solid waste, okay? Because the traditional ways of collection and landfilling, and then nowadays in Brazil we do a lot of biogas and capture and biomethane, and we usually use our biogas from landfills in the big cities, all right? But when we talk about small cities, where we really struggle to recover waste for a better solution. And regarding the organic fraction of the municipal solid waste, I really was trying to figure out how this innovation that you bring to the table can mix the organic fraction and the sewage for a better final solution for these small communities all around Brazil.
Yes, thank you. So indeed, the recovery of carbon, organic carbon, in the form of biogas or biomethane. In fact, I completely agree. It cannot happen effectively below a certain size scale. This is reality, right? You face it. So which is where again I'm going to just rely on one of the slides that I had. So sorry about that. Yeah. The point is, screen sharing has stopped. Okay. Let me just go back to this. It's okay. Can you see the slide?
Yes, yes.
Yeah. So the point I had wanted to make is essentially this. There are other options available that allow us to intensify the recovery of organic carbon, even at smaller scales. This is, and essentially the point is, instead of taking the carbon from where it comes in all the way to methane, if we stop the carbon from going into methane, just that one last step, if we stop the last step, we end up with a process called fermentation. And through fermentation, anaerobic fermentation, the products of anaerobic fermentation, the organic carbon products of fermentation are actually in the liquid phase. So those liquid phases can be concentrated, and then there is a possibility of making fermentation-based recovery of carbon feasible, economically feasible at smaller scales. At smaller compared to biogas. It's still going to require, we cannot do this for a single household. But if we are talking about, there will be a certain scale which needs to be quantified. And then that's the process. And then we have to look at what kind of endpoints would be of interest. If we are talking about, the beauty of fermentation is that we can even talk about production of chemicals for cleaning, chemicals for use within a certain boundary as well. So I would suggest to consider anaerobic fermentation as one of the options for small scale organic carbon recovery, which I think will be more effective than biogas. But again, this is where there is need for innovation. I did visit even during one of my first times in Brazil in a plant in Rio de Janeiro, where it was a pilot plant where they were looking at converting the organics into bio oil instead of biodiesel. I don't know what is going on there, if there are other projects like this, but fermentation could be an option. There could be others as well. There are technologies like hydrothermal processing and other liquefaction technologies, which could be pyrolysis as well, which might be an option. But these are just different options. We'll have to see how they fit, if they fit into these different questions.
Thank you, Professor.
Thank you.
Professor, não sei se colegas da audiência queriam fazer pergunta. Any questions from the audience? So, Professor, I have one more question. I saw some work over here in Brazil trying to, I would say, mixed up sewage from the agricultural side, from the cows, from the porks and so on, with sewage that came from human sewage, basically in order to foster the potential for energy. I'd like to hear from you other servers on this field, mixing, I would say, this potential, because as you probably know, Brazil has a great potential on the agricultural side, and that could be another way to increase the energy that we could create from this enriched water.
Thank you for using the term enriched water instead of wastewater. That we should all learn. Yeah, so combining different feedstock for the production of different endpoints, including energy, is quite attractive. What I have seen in the US, at least, is a combination of food waste with sewage sludge, both primary and secondary, co-thickened, and even this is actually being done quite actively in New York City at a plant called Newtown Creek, and that plant is energy positive. And even if they are looking at biogas, and so the rest of the energy is fed back into the grid. And there are many, many examples like this. This is what we need. This is exactly what we need. If we are now thinking about doing beyond tertiary treatment for reuse, those systems become more and more energy intensive. So then we have some options available to us. Do we keep going back to biogas? If it works, why not? Can we think about other, even more favorable energy endpoints perhaps as well. So it'll be, yeah, we do have the opportunity to mix streams. Our project in Ghana, in fact, we initiated that project, those anaerobic fermenters, by putting in abattoir animal waste to start that process, and that was the most efficient and effective way for us to go forward. So there is a benefit, and this is the straight black and white technology based answer, right? In reality, it is getting access to those streams. So in the agricultural sector, in rural agricultural sector, combining, we have to see what is possible. If it is possible to combine a human waste with animal waste, then there is no reason why we should not be doing it. We also have to find a way to use the energy that is produced. So I think one of the questions was, what is the resistance, or what else can we do better? Before we even consider some of these technologies, I think we have to have a very good idea in terms of the market, in terms of where the end products are going to be used, and how easy it is for us to access the feedstock, and then and where does that technology fit in. But all of these are positive enablers, actually. But I would also like to add, see, our bottom line, our goal is to make sure that we do not spread disease and minimize the spread of pathogens and let's say antimicrobial resistance markers and so on. We have not talked about that in too much detail. We are assuming that some of the technologies that we are discussing now will handle those. And if that is the case, that's well and good. But we will have to make sure that we hit the health indicators as well. Once we do that, recovery, circularity is perfect. But we can't forget the health side of things as well.
Can I again? Sorry, guys. Can
Yeah,
I
yeah,
again?
please.
Okay, thank you. I think Professor said something very important about risk, human risk, pathogens. When we talk about water reuse or sludge reuse, so here in Portugal, not only in Portugal, but now in European Union, the legislation it's obligated to study the risk, the human risk in agricultural applications for water reuse. So the legislation is very clear and very good, but you have to do the study about risk. So there is a proper methodology, not the QMRA, quantitative microbiological risk assessment, but semi-quantitative. So this kind of methodology is like a photo about the project, not so general like QMRA. So I think it's very, very important to discuss this, because when we talk about water reuse in Brazil, there are, of course, the factor yuck. Everybody, the last 2 weeks in Brazil, Sabesp, you know Sabesp, Professor? Yeah. So Sabesp announced the project about indirect potable reuse, because São Paulo now is in a dry scenario. So they need other different possibilities. So they announced the project, and it was like in social medias, some politics discussions, because of the lack of knowledge. Not because of they don't know what is wastewater treatment. They don't know what is water reuse, even of course, for indirect potable reuse. So it's important to highlight this point about risk, and zero risk doesn't exist. So the risk, we have to work with this risk. So we have many possibilities, like barriers, and other things to reduce the risk, but the risk exists. So it's important to explain for the population, for the people, and even the technical professionals, because it's so I think this example of Sabesp, I don't know, guys, in São Paulo, if you heard about it.
Surely. I followed the discussion in social media as well, and I recognize the factor react that you mentioned. That was the idea of asking about resistance against that kind of innovation, not only developing, but developed countries as well. Ana Lúcia?
Well, I think we are running out of time. So, Professor, many thanks again to Anna, to our colleagues over here. Professor, just to finish, and if you could give us a more personal message for us and for the students here, I'd like to know a little bit more what have enchanted you to work with sanitation, why you are so passionate about sanitation and these studies, and connecting with the question of Professor Sergio, what's the importance that you see when you are one of the first that connected microbiology, engineering, and innovation with sanitation all together? So thank you again, Professor, and if you could ask more this personal question for us.
Yes, why not? It always makes us think, right? So I'm not trained as a classical microbiologist. In fact, I hated microbiology. I wanted nothing to do with microbiology. So my training was in chemical engineering. But then I took it upon myself, and so therefore what happens is there is always this need to go deeper and deeper and deeper, because I was never formally taught any of this, and that I think allowed me to make some of these links between biology and engineering. But then also, the way our backgrounds also impact us. I grew up when we didn't have access to water 24 hours a day. We would get water maybe 2 hours in the morning, 2 hours at night. There's also lack of energy. So I think all of this inherently has shaped how we think, how we do, what we do. And I don't have there are a few moments in time that were sparks in terms of what to do, how to do. This connection essentially to take away the concept of if someone is born in a certain socio-economic setting, that should not be used as an excuse that they don't have water and sanitation. So that to me, that still resonates with me. Anything I can do while combining science and engineering to overcome that, I think that is one of my core inherent drivers. So yeah, we are all still on this journey. It's by no means close to an end. Maybe we can do a lot of this together as well.
Thank you, Professor. Anna, as well, if you would like to do any closing remark, saying about your journey with reusable water in Portugal and Brazil. Thank you again.
Thank you, Professor. Thank you, everybody, for the this meeting and for this conversation, very inspiring conversation. Yes, my research and my actions are now in water reuse. We have an institute, it called Professor Chandran, Instituto Reúso de Água in Portuguese, but in English is something like a Water Reuse Institute. So we are NGO, a non-profit organization. We are founded here in Portugal in an international cooperation approach with Brazil. So our objective is to produce and share and manage the content about water reuse based on technical scientific knowledge. So because of this factory and the dissemination of the content of the dissemination and the dissemination of the water reuse with responsibility and safety action. So it will be a great pleasure if you and the guys and the people here that are watching us, if you want to know a little bit more, we have a website and social media. And thank you very much again. I would like to say that now is the moment to change the mind. We have to change the mind now because the future of water is very uncertain, and we have to act now for the future more equal for everyone. Thank you, guys.
Also, one final words from our other colleague over here, Alexandre, please.
Thank you. Just I've been in the sanitation and waste sector for the last 25 years, and I already made a lot of big projects like waste to energy and biogas from big landfills and new landfills and sanitation programs for the big cities. And nowadays, I really think that the next big step for us is try to figure out and arrange solutions for the small communities far away from the big cities, right? Mainly in the Northeast and in the North, where they are still struggling. They are poor, they don't have money to pay the bill, all right? So we really need to figure out different ways to make business in these sites. And that's my new journey it's coming up now, right, in a new company. And sure that the big cities, there is a lot to improve in sanitation at all, in all fields of sanitation, not only water and sewage, but also solid waste. But I really think that the main target now is these small cities.
So just to say thank you again for everybody. And as Professor Jasna just mentioned before, let's keep talking. That's a permanent assembly, a permanent journey. Thank you again for you, Professor Chandra, Anna, colleagues over here. Thank you again.
Thank you. And I'm sorry I could not make it. It was a great pleasure to be part of this discussion. Thank you.
Thank you. Thank you.